A very good afternoon to all of you. My name is Sohail and I work for Airtight Networks. I'm a Wi-Fi security researcher. And today I'm going to talk about a security problem in WPA Too protocol. You may have heard about Hole 196. In fact, in last 1.5 weeks, a lot has been said and discussed about Hole 196 or GTK vulnerability. And in fact, a lot of speculations have been seen around this problem. So today we are going to present the real picture and we will help you understand or see the implication of the problem. So let me answer the most frequently asked questions that people have asked to me is, where did we find this Hole 196? And for your information, it's already there in the standard. For last 6 years, it was buried in the standard on page number 196, and that's the reason why we are calling it a Hole 196. If you see the last line of the page 196, the designers of .11 have warned about the weakness of WPA 2, one key that is used in WPA 2. And on the last line, there is something mentioned about that key. GTKs do not have this property. So designers are talking about some property of encryption key which is not there, which is lacking. But this problem was never discussed, and in fact, there is a problem, but it was never brought to the attention of WPA 2 users, right? So we will, in this presentation, we will talk about that. So this talk is not about unauthorized user taking or gaining access to your corporate or your trusted network. No, it's not about that. It's not about key cracking, okay? It's not about cracking private key of a user. This talk is about an insider attack that can be carried by a malicious user who is already part of your network, who is already inside the network. But I have seen people saying that, okay, when a malicious user is already inside the network, then he can do pretty much anything or everything in that network. Okay, so what's the big deal? Fine. So let me ask this question to them. Let's assume that if you are a malicious insider, can you really sniff private data of other Wi-Fi users? If you try to capture packet in the air, you will see encrypted packet. And since you don't have key, you will not be able to decrypt it. So can you really sniff or see private traffic of other Wi-Fi users even if you are inside the network? And the trick to do that is basically one can try launching man-in-the-middle attack, and the most popular trick is basically in Wi-Fi network is setting up a honeypot. Okay, using this one can actually do man-in-the-middle and try to capture all the traffic of a user. But in a WPA 2 networks, client devices are actually configured to connect to WPA 2. Okay? So those clients are not going to authenticate honeypot access point, or they will not connect. So this trick is also not going to work. So what are the other options available? So probably we can think of launching man-in-the-middle attack in a very conventional style, old style, with the help of ARP spoofing attack. But today's network are basically much more secure than what it used to be. There are security systems which can actually detect ARP spoofing attack. Wired IDS, IPS, or even switches have capability to detect it. Okay? So if you are going to launch ARP spoofing attack, the chances of getting detected is very, very high. Okay? So now let me ask again this question, that without getting detected, can you really sniff private traffic or data of other Wi-Fi users, even if you are inside that network? Is it really possible? The answer is yes. In this presentation, I am going to show you that it is possible. And this will not involve any key cracking or brute force. How? Let's walk through the presentation and we'll see. So I'd like to briefly talk about WPA 2 protocol. I'm sure many of you must have a good technical understanding of that, but just to recall, in WPA 2 protocol, there are two types of keys which are used for traffic encryption, packet encryption. One is called PTK, pairwise transient key. And the other one is GTK, group temporal key. And the purpose of PTK is to protect unicast traffic. Okay? While the purpose of GTK is to protect broadcast or multicast traffic. So there are two types of keys. If you see, PTK is a unique key. It is unique for each user and it is derived per session. So for example, if two clients are connected to a WPA 2 enabled access point, both of these clients will be using two different keys. So client 1 will not know the private key of client 2 and client 2 will not know the private key of client 1. So their traffic is basically secure. But GTK is a shared key. It is shared among all associated client devices. And it is actually managed by access point. So whenever a client connects to access point, it receives a copy of GTK from access point. Okay? So at any point in time, all associated clients are going to have same copy of GTK. Now, I said GTK is used to protect broadcast traffic or multicast traffic. So in a Wi-Fi network, if you have noticed, all broadcast traffic is basically sent by access point, because access point can talk to each and every client. Okay? And this traffic is never sent by a client device, because client can, whenever a client has to talk to other Wi-Fi client device, it first sends packets to access point. Okay? So for a client, destination is always fixed, which means client always send unicast packet, and that gets, so does that mean client never generate broadcast packet? It generates, but in .11, that broadcast frame gets mapped to unicast frame. Okay? We'll not talk about that, but just to, you know. So, which means by design, GTK is going to be used as a one-way key. Access point is going to use it for traffic encryption, broadcast traffic encryption, and all client devices are going to use it as a decryption key. And that's how the software in access point and clients are programmed. And here I'm showing you a log of Wi-Fi client device. There is a software called WPA Supplicant which runs on client devices, and it shows that client has a copy of GTK available, right? So the group key is always available to client device. It is always known to client device. Why it is available? Why client keeps a copy of GTK? Because it has to decrypt packet coming from access point. Okay? Now let me ask, what is stopping that client not using that GTK for its own packet encryption? So protocol says something which is a normal behavior, right? Client should not use this key for packet encryption. It should always use this key for packet decryption. But a malicious user can always exploit this key. A malicious user present in that network can always use this key to create its own packet, generate its own packet. Which means for a malicious user, one broadcast frame is available which that malicious insider can generate is created and send that packet to all other Wi-Fi client devices. But Wi-Fi client devices are programmed to receive packets from access point, not from other Wi-Fi client device, right? So, in order to successfully deliver that packet, this insider is going to spoof the MAC address of access point. Okay? So once the attacker keeps the MAC address of access point as a sender of that packet, all clients present in that network and associated with the same access point is going to receive that packet and going to decrypt it successfully, right? Which means a malicious insider has access to a broadcast frame which it can create and generate and send, and there is no way for other Wi-Fi client devices to differentiate whether this packet is coming from other malicious user or it is coming from access point. Absolutely, there is nothing present in that packet which can help a client to, So it's clear that attacker can send broadcast packet, so he can do a lot of attack. It depends what kind of attack payload he is going to encapsulate inside that broadcast frame, right? So in this presentation, I'm going to show you 3 exploits of GTK. And the first exploit is basically using the ARP payload to encapsulate and create broadcast frame. So in this example, attacker is generating its own broadcast frame and sending that frame to other Wi-Fi users present in that network, and basically the attacker is advertising that he is a gateway of that network. All other clients are going to receive that packet and update its ARP cache, thinking that the gateway, this new machine has become the gateway of that. That's how our protocol works. If you advertise that you are a gateway, all recipients of that packet is going to update its ARP cache. Okay? So attacker becomes the gateway of the network for that client who receives that packet, and after that all traffic generated from that victim is going to be destined to this new gateway who is the attacker. So victim sends all its packet to access point, encrypting its packet with its own private key which is known to this user or access point. So access point will be able to decrypt those packets. And at this point, access point finds that this packet is actually destined for other Wi-Fi user who is also part of the same network. So access point forwards that packet to other Wi-Fi user, and that other Wi-Fi user happened to be a malicious attacker, right? So finally the packet reaches to that insider. So just by injecting one spoofed gratuitous or ARP request frame, the attacker is able to redirect all the private traffic of a legitimate user in that network to its own machine. At this point, attacker can actually drop all the packets and do denial of service attack in the network. But he wants to steal information, right? So for that, he has to provide a seamless service to the user, a transparent service to the user. User should not feel that there is something wrong going on in that network. For example, if I am accessing Yahoo and I am not able to access that, it means there is something wrong in that network. So what happens at that, attacker is going to forward all that packet to an actual server or gateway, and he becomes man in the middle, right? So just by exploiting the GTK shared key and forging its own broadcast packet, attacker is able to redirect private traffic of other victim to its machine and able to provide services. Since attacker is sending a broadcast frames, it means all other Wi-Fi client devices which are also present in that network are going to receive that packet and update its ARP cache. So attacker is not just victimizing one Wi-Fi user, he is victimizing almost all Wi-Fi users who are in the range of that attacker. Now one can ask, what is the difference between this and the old style, conventional style of ARP spoofing attack. Okay, one can, no matter what, no matter if you are using a WPA Too network, I can always use ARP spoofing attack. I can always launch ARP attack to do man in the middle. So in this old style ARP spoofing attack, your packet first goes to access point. And after that, access point decides and forwards those packets to wired segment of the LAN or wireless segment of the LAN, which means the security systems present on that network, wired IDS or IPS or switches, are going to see that packet, which means the footprint of the attack is available on the wire, and in any wired security systems which are capable of detecting ARP spoofing attack are going to capture that packet and detect this attack. Okay? But then when attacker is using this stealth mode attack, packets are directly sent by one malicious user to other Wi-Fi users in that network. Packets are never going to access point, and it is never reaching to wired segment of the LAN. Right? Which means the footprint of attack is limited to the air. Which means most of the wired IDS IPS systems will not detect this, because packet is not hitting the wired segment of the LAN. So without getting detected, attacker can do man in the middle attack and steal private information of other Wi-Fi users in a WPA Too network. Okay? So this is one example of GTK exploit or Hole 196 exploit. I'm going to present here the second exploit. And it's all about, changing the payload, what kind of payload you are encapsulating in that broadcast frame. So this time, attacker is going to use unicast IP payload inside that packet to basically launch IP level targeted attack. So for example, if frame is at layer 2, frame is broadcast, but I can always use IP layer 3 unicast frame inside that. And one example could be, port scanning. If I am going to use a payload which is used for port scanning, then my packets will actually reach to the victim, and victim will respond to that packet, which means I can do port scanning and I can find out whether that Wi-Fi user is vulnerable or not, which can further be exploited. So just think what else is possible. If I know that this payload is going to cause some buffer overflow, then I can inject that packet. Right? I can also inject malware. So a frame is available in which attacker can encapsulate payload of his choice and cause serious damage to other Wi-Fi users. This is the second example of GTK exploit. The third example of GTK exploit is related to the replay detection in WPA 2. There is something called replay detection in WPA 2. So all encrypted data frames have there is a field called packet number, which is a 48 byte number. And this number is going to be present in all encrypted data frames. And this number is used to detect whether a frame is replayed or not. And how that replay detection works? When client connects to access point informs that client that this is the last consumed packet number, so you should use this number for replay detection. So for example, last consumed packet number was 700. Client is going to cache that number, save that number, and after that client is expecting data frame having packet number greater than 700. So for example, if I am replaying a packet which I have captured at the time when packet number was 600, and if I am replaying that packet will not be accepted, because client will find that the packet number is less than the last successfully received packet, which was 700. When access point sends packet, it will send with 701, because that is part of its traffic stream. It has already sent 700, so next packet will be 701, 702, and so on. So when access point sends packet with 701, client is going to accept that packet, and once the packet is successfully decrypted, client is going to update its locally cached packet number. So now the packet number becomes 701. And that 700 number 1 will be used to detect replayed frames. So attacker is going to exploit this replay detection logic. Here what attacker is doing, he is injecting a very large packet number, arbitrarily generated number, because it is a 48-bit number, right? So let's take this example in which client, the last successfully received packet number was 780. At this point, attacker is injecting a packet because attacker knows the GTK. He can create its broadcast frame. He can put any number of his choice. So he's going to put a number, let's say 9,999, 949s, okay? Client is going to accept that packet because at the time of replay detection check, it finds that packet number is greater than the last successfully received packet number, which was 780. So the client is going to update its locally saved packet number, and the local packet number becomes 9,999. Access point has no idea about this change which has happened on the client device. So access point will send broadcast packet as per its own traffic stream. So the last packet which sent by access point was 780. So next time it will send 781, 782, 783, and so on. But let's see what is happening at the client device. Client device finds that the numbers are too less to the locally saved packet number. The last saved packet number was 9,000 and I am getting 781, which means somebody is replaying packet. So client device is going to drop all the broadcast packet whose packet number is less than its locally cached packet number. Now imagine the implication of this. All Wi-Fi client devices who have successfully received attacker injected high packet number will start dropping all the broadcast packet coming from access point, which means the protocol which works on broadcast packet will not work, right? Two clients will not be able to communicate with each other because they will not be able to resolve ARP. So attacker, by exploiting this replay detection logic, he is causing denial of service attack in downlink direction, and which can break few protocols. So this was the third example of exploit of hole 196 or GTK vulnerability. Now I will talk about the POC code that was written to exploit GTK. And I have used two open source software. One is WPA supplicant software, and I have used it. There was no modification done, so it was used as it is. And then I have used open source driver, Mad Wi-Fi. And the main modification was done in the driver part of the Mad Wi-Fi. So before we actually see what kind of modification was done, let me quickly present the .11 frame here. When a client sends a packet to access point, it is called 2DS frame, okay? From client to access point, uplink packet. And when access point sends a packet to client, it is called from DS packet, or it is a kind of downlink packet. And there is a field present in the frame which indicates about the direction of frame, whether it's going from client to access point or it is coming from access point to client, okay? But if you notice, there is not much difference between 2DS frame and from DS frame. If you do a cyclic shift, 2DS frame will become from DS frame. You move address 3 to address 1, address 1 to address 2, and address 2 to address 3, it will become from DS frame, right? And this requires 3 lines of code to do that, and 1 line of code to change 2DS flag to from DS flag. So in 4 line of code, you can actually convert 2DS packet into 4DS packet, from DS packet. And then you need to select a right key to encrypt that packet, because client always use unicast data traffic, so it always use unicast key. So 6 lines of code were added to choose right key. So it's just about selection, in which data structure what kind of key is stored, right? So in just 10 lines of code, it was possible to exploit the GTK vulnerability. So now I will do a demo of man-in-the-middle attack in which GTK vulnerability will be exploited. And after that, I will talk about the countermeasures. So in this example, the demo that I am going to do now, I'll be using 2 Wi-Fi client devices. One client device is going to be the same laptop which I am using for presentation. And then I have one more laptop here, which is running Backtrack. And I'm going to use one of the tools available for launching man-in-the-middle attack. There are a lot of tools available using which one can launch MITM. So, for example, these are the tools, very popular tools which are used to launch man-in-the-middle attack. So I'm going to use one of the tools. So the only modification, the only soft code changes that was done was in Mad Wi-Fi driver. Everything is available open source. I have set up one access point here, and you can see the SSID of that access point is corporate Wi-Fi, and if you go, you will see that this is a WPA 2 configured. This is a WPA 2 access point. Okay. So I'm going to access my attacker machine with the help of VNC software so that you can also see what's going on the attacker machine. Okay, so my machine is accessible, so we can access this. So this is the Backtrack running machine which I am going to use to launch attack. Okay, perfect. Is this visible to people at the back? Or should I increase the font size? All my stuff is here, and I have two Wi-Fi interfaces running on this laptop. One is running on top of unmodified version of driver. I will be using it to demonstrate something, and then I have H0 interface, which is running on top of a modified version of driver. So I'm going to use SSL strip software to launch man-in-the-middle attack. Okay. Okay, so I'm able to successfully run SSL strip tool. Now, the next step is to basically poison the ARP cache of the client, right? And for that, I'll be using the modified version of driver. So, and let's quickly check what is the default gateway present on this subnet. So default gateway is running on 172.16.8.1, and if you check the ARP cache entry, you can see the default gateway is running on 8.1, and the MAC address is basically the last 2 bytes is FE72. Okay, and we are going to replace the MAC address, the IP and this MAC binding with the attacker's MAC. So Wi-Fi users, the IP address of user to which I am going to victimize is using IP address 172.16.8.218. So I have used his IP address. And this is the MAC address of my machine. And this is the IP address of gateway on behalf of which I am sending this spoofed ARP request packet. Now let's go back and see what is the ARP entry. So if you remember, the last ARP entry for gateway was, the MAC address was FE72. Now let's quickly check. And you can see the MAC address of the default gateway has changed. It has become 0AD3. Okay? So far everything is working fine. Let's hope SSL strip works as per the expectation. So I'm going to open some site. Let's open, let's say, Gmail. Oops. Let's try running. Sorry? Okay. So looks like I've not been able to successfully run this SSL strip, but I was able to poison the ARP cache entry of a victim. And just to demonstrate that my packets which I'm injecting is not actually flowing on the wire, I'm going to take a packet capture. Here you can see right now I'm sniffing on a wireless interface of my client, and you can see ARP request and responses frames are being exchanged between my client and the attacker. The attacker was sending request frames and my machine is responding to those requests. Now let me quickly connect a wire and we will sniff what kind of traffic is flowing on the wire. And here you can see there is no broadcast ARP request packet coming on the wire. The packet which I was injecting, those packets are directly going on the. These are the response which is basically sent by my client devices. So the footprint of attack is available only in the air. It's not available on the wire. Okay. But if I instead of using a modified interface which was running on top of a modified version of driver software, if I run unmodified version, what will happen? So let me quickly, so in fact I have demonstrated that my packets are not actually running, going on the wire. Let me quickly present all basically countermeasure techniques. The real fix is basically fixing this problem in the protocol, and for that one can think of deprecating the use of GTK and group address data frame. The other solution is basically using the endpoint security software like SNOT or ARP Watch, which detects ARP cache, a change in the ARP entry, but there is a limitation of this software. It is not available for all kind of Wi-Fi devices. Then one can actually think of using PSPF for client isolation feature, but then this can also break the legitimate communication between legitimate users. For example, if a user wants to share some pictures from laptop to smartphone, that kind of thing will not be possible. And we can probably not use this feature in a voice over Wi-Fi deployment scenario, because then two Wi-Fi client devices will not be able to communicate, which means this will create a problem. So can we really think of using wireless monitoring system? Since the footprint of attack is available in the air, it is possible to detect that in the air. So WIPs can also serve as an additional layer of security in detecting and protecting from such attacks. So the final conclusion is that all WPA 2 networks are exposed to hole 196, and the inter-user privacy that was guaranteed is now broken in WPA 2. The real fix is to fix this problem in the protocol. In the meantime, enterprises can think of using PSPF kind of feature, but for endpoint security, you can use a SNOT or IPsec. But then you say it is not foolproof. In some certain scenario, it will not work. So multi-layer of defense, multi-layer of security is required, and probably over-the-air security can be used to detect attacks like hole 196 or any zero-day vulnerability. So the final words: be aware, be secure. That's it.